Thank you so much, Christine, for the introduction and for this conference. So I'm going to talk about a project that we've been working on with Emilia Divenkova, Matthew Graydon, Heman Kajyar, with Ray Laflamme and Joel Waldman. And the name of this ongoing project is Platonic Ququart benchmarking. So I'm going to first start by giving an outline of my talk. So I will start talking about our system, which is a 4-level system or a Ququart. And I'm going to introduce the control that we have on the system that we are interested in, benchmarking the Platonic rotations that I will introduce in a few moments. Then I will talk about how we are benchmarking our Ququart system, and I will explain a little bit about the implementation in experiments of our 4-level system. And I will conclude with some perspectives of this ongoing work. So, okay, to begin with, we have this 4-level system, which is a spin 3/2. And this system has some interesting features like increased information capacity, higher noise resilience, but it also comes with the counterpart that the Hilbert space is bigger, so it makes the control more complex. So the objective of all this work is to benchmark the noise in the system to study how we can accurately control this 4-level system, and to study some of these properties. So let me define the control that we have on our 4-level system. So we are interested in studying the groups, 3 groups, that are the groups of rotational symmetries of the Platonic solids, that are the tetrahedron, the octahedron, and the icosahedron. These groups have different number of rotations. The simplest one and the smallest one is the tetrahedral group, which has only 12 elements, which makes it easier to implement experimentally. So this is the first group that we've taken a look into. Then we also have the octahedral, which, if we go to the case of QuDits, is the Clifford group, so we can use this group to compare our results in Ququarts with all the results that we have benchmarking QuDits for the case of a Clifford group. And finally, we have the icosahedral group, which is the biggest of all of them, and so it relies on having more accurate control. We have more rotations that we are doing, but we found that in this case, the decomposition of this control of this group is simpler than the others. So that's why we've been working on the 3 of them and comparing the dynamics on all of them. In this talk, I'm going to focus on the first one, the tetrahedral, which is the one that we've been working the most, and we have some preliminary experimental results to show. So I am going to explain a little bit of how these symmetries work. So as I said, the tetrahedral group has 12 rotations, 12 elements, right? One of them is the identity. Then we have 3 pi rotations, which might be a little bit tricky to see in 2D. I tried to bring a tetrahedron, but I couldn't find one, so yeah. But basically, these rotations go from one edge of the tetrahedron to the opposite edge of the tetrahedron. There is an axis that goes through the middle point of these 2 axes. And if you do a rotation of pi around that axis, you have one of the symmetries. And because we have 6 axes, this gives us 3 rotations on pi. So we have 6 edges, and that gives us 4 rotations of pi, because each axis connects 2 of the edges. And then we also have another type of rotations, which are rotations in 2 pi by 3 and 4 pi by 3. And these rotations go around axes that part from one of the vertices of the tetrahedron, and the other extreme of the axis will be going through the the middle point of the face of the opposite part of the tetrahedron. And in that case, we have a triangle, so we are going to have that symmetry of changing these three vertices. I'm not sure if this was very clear. If you're interested, we can talk a little bit more about how these symmetries work. But basically, what we are going to do is apply these rotations, which are around axes that are defined, like x, y, z, and then axes that have a combination of these three x, y, z. Okay, so now I'm going to explain a little bit more of how we are benchmarking our Ququart. For that, we are using a protocol that's well known. That's the randomized benchmarking protocol, or RB. One interesting thing about this protocol is that it's independent of state preparation and measurement errors. And it's been extensively studied in QuDits and also in QuDits in recent publications. So the idea of this protocol is to use randomization to study the noise. So to use this randomization, what they do is they perform n random rotations of a given group, and then at the end of all these rotations over, in our case, our Ququart, we will have an extra rotation which will go back to the initial state. And at the end, they are going to measure the survival probability or the success probability of this sequence of n+1 rotations. This probability is going to allow them, in some cases that I'm going to explain in a bit, to get the average gate fidelity, which is our objective. So this average gate fidelity will give us an idea of the gate error average over all possible input states. So in the case of a qubit, in particular for the Clifford group, because the Clifford group is a 2D sign, this protocol behaves nicely because a 2D sign, which is a group that's a 2D sign, is going to average any kind of noise and make it or convert it to a depolarizing channel. So in the end, if we measure the survival probability after this sequence of random unitaries, what we are going to have is an exponential decay, which will decay with the number of unitaries n, and the rate of this decay will be directly related to the average fidelity that we are interested in getting. However, for a Ququart, and in many cases for a qubit, when it's not a 2D sign, this doesn't work. So neither of the groups that I've been talking about is a 2D sign. This means that this randomization procedure doesn't fully depolarize the noise, but rather divide the noise in different spaces, which are going to decay, each one of them with a different rate. So we can still get the average fidelity at the end, but we need to know all the decays, which would be like a multi-exponential fitting. And we also need to know to which space each decay belongs to. So this makes it impossible to use standard randomized benchmarking to study our noise in the case of a Ququart. So what we did instead of that was we used another protocol which is very similar, and it's called character randomized benchmarking. So the idea of character RB is to change the protocol just a little bit and then add a little bit of post-processing to filter out from this multi-exponential all the decays except one. So in this way, we are going to be able to find each decay f sub lambda that we are interested in at a time. So we are going to do many experiments and find all the parameters that we need to get our average fidelity. Okay, so to explain a little bit more in detail about these two sequences, these two protocols, I'm going to show first, okay, the sequence of the standard RB. The standard RB will begin with the initial state preparation. Then we are going to apply this n+1 unitaries that I said. and we will finish with a measurement. The parameter that we are going to measure is the survival probability that you can see there. Yeah, there. And as you can see, this is a sum of many exponentials. So here, these f lambda I are going to be the decay parameters that we are interested in. And here we have this is an overlap that I'm going to explain in a minute, which will give us the intensity of the signal that we have. So this is going to be just a parameter in the fitting 2. But in this general case of a standard RB, we are not going to be able to extract all these parameters from this multi-exponential fitting. So here, in this overlap, what we have is, first, we are using the Liouville representation, which is we are writing the density matrix, which is in a Ququart state, 4 by 4 matrix. We are writing it as a vector of 16 elements. And then we have here the measurement, which we are defining an inner product here, which will be just the overlap between the initial state, how it evolved, and the measurement that we are doing. And in the middle here, we have the projector over the different irreducible representations. So what does this mean? Okay, so we have groups. In order to apply these groups in our Ququart system, we need a representation from these groups to the Hilbert space that we have. This representation, we are going to use the adjoint representation, and it can be decomposed in smaller parts, which are called irreducible representations of irreps, which are these pi here. And each irrep can occur more than once. So there could be some multiplicities of each one of these irreps. This decomposition is very important because all the action of the group is going to be carried by these individual irreducible representations. And that's why we are interested in seeing this decomposition and how this decomposition separates the noise at the end of the sequence. Okay, so the difference with the character RB sequence that we have here is that we add an extra unitary U0 or U0, and we compile it without noise. So what we do is the first unitary that we apply will be the multiplication of the first U1 and this other U0. And then doing a weighted average for all U0, what we end up having is this survival probability, which, as you can see, is again a multi-exponential fitting, but only on the multiplicity of each one of the irreps. So if we have an irrep that occurs only once, we will only have one exponential decay to fit there. And that's the idea. We are making our fitting of these many parameters as simple as possible. And for that, we have to repeat for all the irreps, because each irrep will give us a different survival probability here. And then at the end, we are going to use all these parameters, f lambda, to get our fidelity, with our average fidelity that we are interested in. I'm going to explain a bit more in detail how the protocol works. So basically, we start with choosing one irrep, pi lambda, with a certain multiplicity. So for that irrep, we have to choose an initial state and a measurement that overlaps as much as possible with this irrep, with the action of this irrep. Then we're going to choose a certain number of unitaries that we're going to apply. And for that n, fixed n, we are going to choose a random sequence in the group that we are benchmarking. So then we are going to compute the inverse of all these n gates. And for the part that is the character RB protocol, we have to choose a random U0, add it to our sequence, and apply all these n+1 gates. Finally, we measure the the observable that we wanted to see, and we measure we get the survival probability, which will depend on the random sequence of gates and also of this added gate, U0. If we repeat this process for all U0 in our group and we do kind of weighted average of these survival probabilities that we got, we are going to find this survival probability, which will be only inside, like taking into account the action of one of the irreducible representations of the group. And then if we repeat this for many different sequences of n gates, random n gates, we are going to have an average of the survival probability for many different random elements. And from this, if we study how this survival probability decays with the number of unitaries n, we can find the parameters that we are interested in, this f lambda I, using a multi-exponential decay. And with this f lambda I, we can get our average fidelity. I hope this makes sense. If there are questions, I will be happy to answer later at any point. But this is the idea of the character randomized benchmarking that we are implementing. And now I'm going to explain a little bit of how we are implementing all this in experiments. So as I said before, I'm going to talk about the tetrahedral group. So we started with the character table. I'm not sure if you are familiar with the character table, but basically here we have the conjugacy classes of the elements of the group. So we have the identity, the 2 pi by 3 and 4 pi by 3 groups of rotations, and then we have the 3 pi rotations. And here we have the irreps. So we have, in this case, 3 irreps that are one-dimensional and 1 irrep that's 3-dimensional. So the first thing that we did to understand all these dynamics is to get the projectors on each one of the supports of these irreps. And we also got the isotypical decomposition of our group in terms of these irreps, which means that, for example, for these 2 irreps, we have only 1 copy in our decomposition, and for this last one, we have 4 copies. Okay, so the next step was to choose the initial states and the measurements that were going to maximize the overlap between with each one of the irreps. So for that, we chose 2 different initial states. Here, this is the first initial state that we consider is a combination of the identity plus the spin operator in Z of the Ququart. And the observable is going to be the same, the spin operator in Z. And we observe that this initial state has only overlap with the last irrep, which is the more complex of all of them. So we started with this one to understand a little bit more about this irrep. And then the idea is to, we are already working on creating this pseudo-pure state. And with this pseudo-pure state and measuring the probability of staying in that pseudo-pure state, we can find that there is overlap with all of them. So we can use character randomized benchmarking to separate all the decays and to get, in the end, the full average fidelity. So we implemented all this in NMR. Okay. So the NMR Hamiltonian is going to have, okay, in our case, we are working with this molecule here, which is the molecule of acetic acid. This molecule has 5 spins that are going to be able to be observed in NMR. We have 2 carbons, C1 and C2, which are distinct, which means that we can address each one of them individually. And then we also have 3 hydrogens that are equivalent. This means that every time we want to control them, we are going to control them together. And then here we have a table where we can see the Larmor frequency of each one of the carbons and also of the hydrogens and the coupling between them. And this is the Hamiltonian. So from this system, how can we create a Ququart? So the idea is what we are doing is basically sum of angular momentum of 3 spin 1/2. As you know, this sum of angular momentum will give us a decomposition in 3 subspaces. One will be the spin 3/2, which is the one that we are interested in because it's a 4-level system. And then we have 2 qubits. So this is just a change of basis. The basis of the states that live here are this one, like in terms of the original hydrogens, are these ones here. So we have our spin is 3/2. The projection plus 3/2 will have the 3 spins pointing up. Then we have, for the 1/2 projection, we have the symmetric sum of 2 spins up and a spin down, and the same, and the opposite would be for minus 1/2 and minus 3/2. So this is just a change of basis, but what we need to do is to project our system to be living only in this part of the space. So to do that, we have a Ququart selection sequence, which here we have the pulses applied in NMR to the hydrogens and the pulses applied to one of the carbons. We can forget about the other one, which is going to be refocused during all this sequence. And here we have rotations around X and also around 2 axes. And what we did was we optimized these 2 axes, A and B, to be the ones that maximize the overlap with the Ququarts and at the same time minimize the overlap with the spins. So after all this sequence, here we have also contribution of the coupling between the carbon and the hydrogens. And at the end, we have a gradient to get rid of some of the elements of the density matrix that we didn't want to have there. At the end, what we have is, from the beginning initial state, which was polarized in hydrogen, so it was all the spins were in Z direction. After this sequence, we obtain the spin operator in Z in the Ququart. So from this point, we are going to talk about only the part of the matrix that is different from 0. Okay, we're going to talk about the part of the matrix that corresponds to the Ququart. And if we observe this in the carbon, we can transfer all this polarization in the Ququart to observe in the carbon, and we can see a spectrum like this one here, which will have each one of these 4 peaks will correspond to one of the states of the Ququart, and the amplitude of the peak will be related to the amplitude of the spin projector in projection in Z. Yeah, and then in red, you can see how the original sequence was, the original spectrum was before doing the selection. And then we also studied which kind of control we have over the Ququart. So in NMR, we know that we can do any rotation in the 3 hydrogens, but it has to be the same for the 3 of them. So we showed that in the Ququart space, this corresponds to this kind of rotation, which has here the spin operator of the spin 3/2 space. And so using GRAPE, we optimized all the group rotations that we have in the 3 groups that we are interested in. And I'm just going to show a little bit of the preliminary results that we have. So here, what I call the reference spectrum after transferring to observing carbon is the spectrum that we get after the spin 3/2 selection. I showed you before 4 peaks. So here, what we have is 8 because we have the coupling with the other carbon. So each one of these peaks is going to be split in 2. And this reference spectrum we are going to use to to get the intensity, the normalized intensity, after applying the sequence of n gates. And using that, we found the survival probability for, these are not many data points. We are working on getting more of them, but we could see that there is, it looks like it could be fitted using 2 exponential decays. And this makes sense because one of our collaborators, Emilia, worked with these irrep, and she found out that for this initial state, we are only going to have 2 decays. So yeah, this is just preliminary, but I think it shows a little bit of what we are expecting to see. So, okay, so in conclusion, this is an ongoing work. Our results are showing a little bit of how we are using this character randomized benchmarking to study the noise in our Ququart system. We could prepare a 4-level system in liquid state NMR, and we are benchmarking the noise using the symmetries of the Platonic solids. Yeah, and we are still working on getting more data to get, at the end, the average fidelity that we are interested in. So these are the references, and thank you so much. I would be happy to answer any question that you may have.